Thank you so much for kind introduction. I'm Toshiaki from Tohoku University. So today I'll talk about integrated synthesis of the graphene and ribbon-based quantum dot. So I'm talking about a quantum dot, but when you hear about a quantum dot, maybe people are thinking about most of the popular one as this one Nobel Prize in chemistry last year. They find a very efficient way to fabricate a very tiny semiconducting nanoparticle which can emit the light, and the wavelength is strongly correlated with the size, and this is a kind of the quantum effect. And in this case, most of this quantum dot is used in the solution-based materials, and many quantum dots in liquid. So this is a very wonderful technique, and which can be applicable for many various kind of applications. But that point of my talk is a bit different from this quantum dot. Because in my case, I'm going to focus on the quantum dots for quantum information devices. What is a quantum information devices? The most popular one might be the spin qubit. In this case, we focus on only one quantum dot, which is exist in the solid devices, and we can control the electron spin in and out of each of the quantum dot. So this can be very useful for future quantum computer or something other new kind of the quantum information devices. And actually about this field, a lot of history also existed, and the gallium arsenide might be the very traditional one and most popular one, which is well established based on the quantum well or quantum wire studies. But recently, relatively new materials are also attracted in this kind of the devices, which is nuclear spin-free materials based on the group 14 elements, carbon, silicon, and germanium. So in my talk, I'm mainly focused on carbon and especially this graphene part to fabricate a kind of the new type of the quantum information devices based on the quantum dots. Okay, so why graphene? So graphene is also another kind of the Nobel Prize materials. In physics 2010, two very famous Professor Geim and Novoselov in Manchester, University of Manchester, find a very unique property of this graphene, which is one atom stick to the seat of the carbon, are composed of this kind of hexagonal network of carbon. And this graphene includes very, very excellent properties in terms of the quantum dot device applications, like a weak spin of coupling and long distance qubit coupling, and also large electron spin G factors. So this is definitely big advantages for quantum devices, quantum dot devices. So I'll just briefly explain the current state of the graphene-based quantum dot studies and how to fabricate the graphene-based quantum dot in the world at the current state. The most popular one is like that. At first, we fabricate a two-dimensional sheet of the graphene by using the conventional thermal CVD process. We often use a copper foil, which can be easily control the thickness of the graphene. Then this CVD graphene need to be transferred to some specific substrate like a silicon or to form the devices by using the polymer capping method. And then we do the kind of etching to form nanostructures which can be useful for our quantum dot devices, and putting the electrode to control our carrier confinement and control the spin properties like that. And actually, by following this three-step CVD growth, transfer, and etching and electrode fabrications, very nice high-quality quantum dot can be already fabricated in the world. This is top data in the world. So it looks quite nice, and this is definitely very beautiful. This is very nice work in terms of the fundamental studies, because how to integrate these quantum dot devices in a wafer scale, like a 300 millimeter scale. It might be possible by using this kind of transfer technique and etching and putting electrode, but in practical way, there's so many problems, like size of the graphene film is limited within few centimeter scale, and the quality of graphene is not super high. So many contamination can be introduced during the transfer technique. So that's why we think that this process itself is not strictly applicable for kind of the future practical application, industrial applications. So purpose of this study is establish a kind of the scalable method for graphene quantum dot devices. How to do that? And here is the strategy. So as I explained, graphene is a two-dimensional seed, but my target is a quantum dot, which is a zero-dimensional structures. So we need to transfer 2D to 1D, 1D to 0D. So we try to step-by-step approaches. And step one, we need to establish the scalable method for position selective growth of the one-dimensional graphene. This is so-called graphene nanoribbon. This subject itself is quite tough. I'm going to explain it later. Then when we can transfer this 1D graphene nanoribbon to the zero-dimensional graphene, which is so-called quantum dot, graphene quantum dot, it can be a kind of the final goal of the large-scale integration of graphene zero-dimensional devices. So yeah, here is a kind of the clear strategy of our study. So I'm going to try to explain each of the part from now. So here's outline of my presentation, and then this is kind of the main result in our project about the quantum dot study. But before we move on this part, we're going to explain about the one-dimensional graphene synthesis, graphene nanoribbon synthesis, which already established by our groups. Okay, so let's start from the graphene nanoribbon fabrication part as a step one. And then, so this is a kind of typical way how to fabricate graphene nanoribbon. So most popular one is just using the etching, top-down approaches, fabricate a 2D graphene using a CVD or something, and just do the electron beam lithography or something, and etching. So yeah, in principle, it's possible to get the like 10 nanometer width of the nanoribbon with this method. But as I explained before, this is not perfectly scalable because of the problem in the initial quality of the graphene seed. Another way is the unzipping of carbon nanotubes. This is also a very unique method, and it's possible to getting very high quality quantum dot and high quality graphene nanoribbon. But this initial material carbon nanotube itself is really difficult to control the position in the wafer. That's why this is also not scalable. And recently, most hot topics about a graphene nanoribbon synthesis is using the organic chemical method. By using special precursors in any form the organic way, they can atomically precise structure control the growth of the graphene nanoribbon like that. This is definitely a wonderful method in terms of the structural controllability of the graphene nanoribbon. However, in this method, they need a kind of the gold substrate for the nucleation. That's why this method also needs the transfer to form to make a devices. That's why, yeah, and also the nucleation site is random, and alignment also random. That's why we can say that this is not so really practical and scalable. So we have to find something new method which can well precisely control the position and alignment of graphene nanoribbon in the wafer. So we think something new idea, and here's like that. So before our studies in our field of the graphene synthesis, a lot of people know that just a kind of the nickel film, just a film has a catalytic activity for the nucleation graphene. So we can easily use a film of nickel for the synthesis of graphene. So simple idea is like that. If you use a one-dimensional nickel as a catalyst, and if graphene can be graphene on the surface of this nickel, that should be graphene nanoribbon. It's quite simple. And we tried many times using the thermal CVD as a first choice because which is the most popular one and very convenient. But always the nickel nanowire is melted during this heating process. That's why graphene nanoribbon cannot be growing with these approaches. But only when we use a plasma reaction, this is a kind of the key technique of our studies. Because of the non-equilibrium reactions, this kind of the reactions happen successfully. And the big benefit of this method is graphene nanoribbon can be directly bridged between the large nickel parts. And this structure is already existed on the silicon dioxide and silicon structures. That's why just after the growth of the graphene, these materials become devices, so-called field effect transistor devices. This is a super big advantages in terms of practical applications. So I'm going to explain detail about our experimental result. So here is a typical SEM images of just before the plasma CVD. We can draw the nickel nanowire using electron beam lithography. So as you know, electron beam lithography controls any kind of structures within several few nanometer or about 10 nanometer scale. So we can control the width, length, and shape any structures using this lithography process. And this nanowire is already bridged with large nickel source and drain electrode, as I explained. And after the plasma CVD, very interestingly, this nickel nanowire structure is changed to the filament-like materials, like this. Sometimes nickel part is partially remain, but most of the part is changed to the filament-like shape. And based on the detailed analysis using FM, SEM, TM, Raman mapping, blah, 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 we can identify this is exactly the graphene. And also the width can be also controllable just by controlling the initial width of nickel nanowire. So this is a very important result. Now we can control the position and also the alignment of the graphene nanoribbon in real devices. and also on the surface of this graphene nanoribbon, nickel does not remain anymore. And as I explained, this graphene nanoribbon is directly connected to the large source and drain on our silicon dioxide substrate. So that's why the as-growing graphene nanoribbon can be used for kind of the FETs without any post-treatment. So this is somehow very promising method for practical method for scalable device fabrication using one-dimensional graphene nanoribbon, which is a bit old data. And at that time, more than 10 years ago, the fabrication yield was not so high because of the very, very tricky method. Nickel nanowire is changed to the graphene. Why? No one knows what's really going on. That's why we need to touch in detail about this kind of the growth mechanism part. And here's like that. With the curve later about the theoretician about the phase diagram analysis, we can identify that the structures of nickel just during the plasma CVD is forming the liquid phase, not solid. And also the stability of the liquid phase nickel is strongly correlated with the carbon density inside the nickel. And then once high density carbon is supplied from plasma reaction, the liquid phase nickel form hydrophilic-like structures. And here is like that. And we start the cooling. And then during the cooling, graphene is segregated on the surface of liquid phase nickel. And at this stage, graphene nanoribbon is formed. But so many liquid phase nickels remain under the graphene nanoribbon. But the carbon density inside the liquid phase nickel become very low. That's why it's changed to the hydrophobic. And hydrophobic liquid is very unstable. Once it's dropped into two pieces, capillary force happen, and then which is opposite direction. That's why this particle move each side of the electrode, and finally suspended graphene nanoribbon can be formed like that. So this is kind of the mystery of what's really going on from the nanobar to the graphene nanoribbon changes. We're not 100% sure this mechanism is really true or not, but just by following this mechanism, we could see that we can say that controlling the carbon density inside the liquid phase nickel just before cooling seem to be very important to control the stability of the and also successability of this process. So we control the carbon density inside the liquid phase nickel just by controlling the plasma irradiation time within few seconds, 10 seconds, 15 seconds, 20 seconds, or something like that. And here is of the plasma irradiation time versus fabrication yield of graphene nanoribbon. Very surprisingly, at the specific growth time, the growth yield is jump up more than 90%. And under the best conditions, here is a typical 2 by 2 centimeter images, and there are more than 1 million of the suspended graphene nanoribbon can be fabricated, and more than 98% of the successful yield. So this is a first time result about kind of the wafer scale integration of the suspended graphene nanoribbon. So we think this is definitely practical and scalable compared from other transfer-based method. So we're going to try to use this unique method for quantum dot applications. So, but just before showing the quantum dot, I just quickly show the other applications. We also tried like kind of non-volatile memory applications or some electric device applications. So, but this is out of focus on my study. So this presentation. So if you're interested in it, just check these papers. Okay, so let's back to the final part. Our main part of my studies are quantum dot fabrications. So as already explained, our strategies, step-by-step strategies like that. Step 1 is fabrication of graphene nanoribbon was accurate position selectivity in a wafer scale, and we did it. So we need to move on. Then step 2, how we can change this 1D shape to the 0D. The easiest way is just make it short and as short as possible. So first we focus on this length of the initial nickel nanowire, and here it's like that. By make it short and short, try to form change 1D to 0D dimensional transitions. And here's a typical data of the device fabrication yield as a function of the length of the nickel. And with increase of length of the nickel, the fabrication is slightly decreased. But interestingly, the appearance rate of the Coulomb blockade, which is a kind of the sign of the quantum phenomenon, I'm going to explain in detail later. But this appearance rate of Coulomb blockade increase with increase in nickel of initial length of nickel. And under the best condition, when we carefully measure the Coulomb diamond properties, this also explained later. If the length is quite long, most of the Coulomb diamond becomes a much dot-like shape, but under the best conditions, between 100 to 200 nanometer length, most of the quantum dot shows a single or few dot-like features. So this shows that the length of the nickel, initial nickel nanowire length, is very critical to change from 1D to 0D as we expected. And this is a typical nice data of the single dot-like features. Here's a drain source bias as function of gate bias voltages, and we plot the current as a color scale. So you can see the blue diamond-like shape. This is a off current region. Current doesn't go through, and this diamond is well close near this zero bias voltage region. So this is so-called a single dot-like features. And when we carefully look at this device with SEM, the whole nanowire is changed to the graphene nanoribbon. But very interestingly, the middle part of the graphene nanoribbon, very fine structures also existed. Honestly speaking, we are not 100% sure what's, what kind of atomic structure is this, but we think this part of the defect-like structures might be formed in the middle part. And this can be formed a kind of the quantum dot. So size is about 12 nanometer or something like that. So, but anyway, by using our method, we show that our fabricated nanoribbon shows a very nice quantum dot, Coulomb diamond-like shape. And also as a demonstration of the kind of the scalability, and also the practical way. For the quantum dot applications, we need to control the electron spin or charge by using the gate. But the previous data was just using the global backgate. So we need to locally control such kind of charge. So we put the side gate in this system, and this process itself is unique because we designed the side gate before the plasma CVD together with the nickel nanowire and just do the plasma CVD. Even after plasma CVD, this side gate is still survive. That's why we can use this side gate for tuning the carrier control without any post treatment. So as grown devices, and here it's like that. A side gate can also change the current flow of source and drain current, and which is very reproducible and very fast, and fast operation can be also done. So what we want to say is this kind of the side gate device fabrication is also possible by using our scalable method. This is one big advantage. And another demonstration is we try to demonstrate the scalability. This is not super big devices, but a kind of demonstration. We put we try to fabricate 16 devices, and we check whether each of device shows a Coulomb diamond or not. And but 9 devices within 16 devices shows a nice Coulomb diamond-like features. So this is a kind of the fabrication yield of the quantum dot device is about 56%. It looks not so super high, but in terms of the graphene-based quantum dot device fabrications, most of the graphene-based quantum dot, as already explained, is such nice devices within so many devices. That's why they don't discuss about a successful rate, but a real successful rate should be below 1% in the real world. That's why this 56% should be definitely higher than the other conventional transfer-based method. And we think it can be increased much more in the future. Okay, so now I just showed our fabricated graphene nanoribbon can be formed a kind of quantum dot-like features. But just showing the Coulomb diamond itself is not enough for the spin qubit fabrication, because for such kind of spin qubit, we need to use up and a down spin of this ground state. So to realize this kind of the spin control, clear ground state and excited states should be appear in this Coulomb diamond features. So we further did the careful analysis by collaborating with Professor Otsuka for real low temperature measurement, and here is the result. This is a 2.2 Kelvin measurement, and as you can see, the clear diamond-like shape can be also obtained. This is a gate bias and the drain source bias voltages of the differential conduction mapping. And then not only the diamond shape, so many multiple straight line can be also appear here and here. So this is definitely a kind of the excited state, and clear energy spreading between the ground state and excited states can be observed in our real graphene nanoribbon-based quantum dot devices. So this is definitely a big advantage in terms of the spin qubit applications. We also check the temperature stability. We slightly increase the temperature, 20K, 50K, 80K. So as we expected, with increase the temperature, each of the line become broadening like that. But at least up to 20K, this excited states can be still survive. This seems to be somehow quite surprising, because usual typical silicon quantum dot, and most of the typical temperatures around 1K to observe the excited states. But our data is 20K, so this temperature difference, the high temperature stability is significantly big differences and a kind of good advantage of the graphene-based quantum dot. And we are not 100% sure why this kind of high temperature stability existed in the graphene-based quantum dot, but this is a kind of the one possible way to explain. So energy levels, but energy between the ground state and excited states can be expressed with this formula. And then the important part is this here, electron effective mass. And here is the calculated data of the electron effective mass of the blue, red line is graphene nanoribbon, and the silicon is here. So this M star is always smaller than that of silicon. That's why the smaller M star in the graphene-based quantum dot should be the critical reason showing such kind of temperature stability. Okay, so just the final slide. I just quickly show one of the big achievement. Based on this, cooperative research project, our proposed project is finally accepted in a JST Quest, a kind of a big, large project, and we started from last October. In this project, I'm a director, and Professor Otsuka is joined as a kind of collaborators, who is also, collaborator in this current project. And also together with Professor Senba at the University of Tokyo, what we want to try to do is try to fabricate a very specific amplifier devices using the graphene nanoribbon structures. And I don't go in detail, but I quickly show that previous devices I just explained as nickel nanoribbon-based devices as for the quantum dot fabrications. So nickel graphene nanoribbon nickel structure is formed. But our new approaches in this project is we use superconducting metal as a catalyst, and once graphene is formed, superconductor graphene superconductor junction should be formed. This is definitely the graphene-based Josephson junction. So we try to use this new kind of devices, which is very scalable for real superconductor quantum computer applications. Okay, so let me summarize my talk. For the 1D graphene synthesis, we established very unique method. It is very scalable. And by using this new technique, we fabricate a zero-dimensional graphene nanoribbon, which is so-called the quantum dot of graphene, and it shows a clear excited state and high temperature stability. So we think that our established new method for the fabrication of graphene nanoribbon-based quantum dot is really scalable, and it can be applicable in a practical way in the future. Thank you so much for your kind attention.
Thank you very much for the nice talk.